Hey, welcome back. Today I have to make these two brackets out of aluminium, and the complexity of these parts and the fact that it's two, in reality it's three, but I already made one and shipped it out. The fact that these are fairly complex lends itself to the CNC mill. So we will do a little bit of manual machining, but most of it will be ran on the CNC mill. It will be mostly about my process and my approach of how to deal with some real CNC parts compared to what I usually do. This is not the kind of work that I usually quote for, because that belongs on a 5-axis CNC. It would be way faster to do that there in one setup. But a friend asked me, gave him a quote, and we both were happy with the quote in the end. So I got the project, and it's a nice change of pace for me to do something like this compared to the usual nightmare work that I get. So let's get started. Today we have to make two flux capacitor brackets that look like this 3D print. Large L shape, round base, two counterbores that are connected, some threaded holes. Each of these features very simple, but everything together makes this quite the annoying part. I already made one for validation purposes to check all the clearances and if the design can be assembled. Shipped it out, it's all fine. So I got the okay to make the other two. So here's the material. I choose to make them out of round stock because that was the easiest to get in a short order, compared to having it sawn out of a plate or a block. So I went into CAD and figured out the smallest possible stock that I can fit the part in. It has to be moved off center, but that's not a problem. This is not a lathe part, this is all CNC with one or two steps on the manual mill. My first problem was how I'm going to hold this chunk on the CNC mill. If I stack it up on top of the 3-jaw chuck, this is going too tall because I need fairly long tools to reach all the way down. So I ordered some spare pull studs from Lang. I'm going to put them in the stock. And this allows me to hold the stock directly on the 0-point system plate of the CNC mill without any additional work holding. And then I have a fixture already prepared for the second side. This is the fixture for the second side. It has also the Lang pull studs on the back side, and the part gets bolted on from the back side. When I have the first side cut, it can go on the fixture like this, and I can cut all of this. Also, I remove a lot of stock on the bandsaw. I even had to mill an additional step into a set of the jaws for the 3-jaw here to grab 110mm stock. Otherwise, this chuck kind of tops out at 90mm. I'm going to use a face mill to clean off the top. Oh yeah, if somebody tells you 40 taper is self-releasing, they probably don't have a clue what they're talking about. A precise fitting 40 taper is very much locking. I'm going to use I think it's 70mm face mill. Surface finish here is not really important. All of this will get removed later. This is just for reference now. Finding the center of the stock, indicating directly on the as drawn surface of the stock. It's quite entertaining because it's not exactly round and smooth, but got it pretty good within 50 micron. This would be center of the stock, and my hole pattern will be offset to here, so it's about like this. Well, you offset by 7 millimeters. I figured out those dimensions in CAD. And the final part will be like this, oriented in the stock. That's wrong. It will be oriented like this. This ear will clear these two holes on the side, I think. Yes. Double checking my print here. So the hole pattern for the Lang 0-point system is 52 millimeters center to center, and that's what I'm going to drill here. Positional accuracy between the holes should be within 10 microns for the Lang system to work properly, otherwise it gets a little bit stuck. So normally these counterbores for the Lang pull studs are super tight. They're really a press fit. In this case I don't need that. They need to be a precise sliding fit. They will be mounted once and removed once. I don't want to... They have a tendency in aluminium to seize up on you if you go with the manufacturer's recommendations. Well, they're not seizing up, but they're like really embedding into the aluminium, and I don't need that here. I want to get them out without major pain. This end mill has a tendency to cut a little bit undersize, so I have a little bit of stock to clear up with the boring head. So the Lang pull studs have a 12.02 millimeter diameter. They taper a little bit, so they really seat themselves in. That works very well in steel fixtures. In aluminium, it wants to seize up even if you put something like molybdenum disulfide grease on them. So I like to overbore them a little bit. As you can see, just from plunging the end mill, there is no way these go in without a hammer or heating the block up. So I have the Woolhop, the UPA boring head here. Let's find a small boring bar. So I ran over to the lathe department and stole a tool from them. This is a shop ground micro boring tool, completely ground on the D-bit grinder, and it has a 45-degree angled cut on the back. Oops. That is aligned with the cutting edge in front here, or with the top rake. Means if there is a cross pin in the bore that you put this in itself aligns with the mold. And I made not only holders for the lathe that have this cross pin. So here is one of the holders for the lathe, and you can see there is a cross pin. Well, and I dropped it. This is also a great table for demonstrations. So let's take the next one. Unfortunately, these don't cost me anything because I grind them out of carbide scrap. So this also has the this also has the alignment angle on the back, and this just drops in this holder. And as you can see, when I hit the cross pin in the back, it self-aligns. And I'm using the same principle with this bushing. This bushing has an 8mm OD, which is the tooling diameter for the boring head. And it has a cross pin in the back. And it has a flat that's aligned with the cross pin. So the boring tool goes in and it aligns itself with the flat here. And the flat aligns with the set screw of the boring head. So there is no need to manually align these tools with the setup. So this drops in here like this. And my boring tool self-aligns. So that's all. No rotational alignment of the boring tool needed. This tool is a little bit longer than I would prefer, but I think it will do. I'm only taking a very shallow pass out of these roughed out Countebores, just to open them up wide enough to accept the pull studs without having to force them in. And that's probably all that we needed. I just took a very light pass with the boring bar, clean up the bore. Let's see oh yeah. Oops, okay. I will leave it like that. It goes in like 2/3 of the length, and then the taper of the pull stud gets big enough to lock it up. And yeah, I'm just boring with the quill. Tapping M8. This vintage of FP1 does not have a spindle reverse, so letting the tap run in under power, and then I unwind it by hand. Also, I'm bottoming out the tap by hand. Okay, there's the whole pattern. I stoned the surface very lightly because this will be our reference surface when we flip it over. This will rest on a 0-point plate, and we don't want anything sticking up there. I like to use a little bit molybdenum disulfide grease on the pull studs and also on the threads when I assemble these. So they come with a loose piece of all thread. So you can either use the the all thread, or you can use a screw from the other side if your design allows for it. But in this case I have to do it like this. Give it a small dab of the grease. And I would just take an impact wrench and drive them in. No, just joking. These are meant to be torqued down with a torque wrench. So over at the CNC mill, this is the Lang 0-point plate, and we can remove those plugs. This is just a magnet. And the stock can just drop onto this plate now. And by tightening the screw on the side here, the stock now is secured to the 0-point plate here. Doesn't go anywhere. Workholding directly on the 0-point plate with the studs in the stock or even in the finished part is quite nifty. We did something similar at my old day job. We had a large 0-point system on a gantry mill, a large-ish VMC, and all the mold bases for, well, large molds had counterbores cut into them for 0-point studs. Very similar to the Lang, but different system, different manufacturer. And that allowed us to put the mold bases for reworking or repairs back on the mill without having to mess around with strap clamps or things like that. That was super convenient. I ordered the stock oversized in length, just in case their saw cut was not as square as it was. Just a little safety measure. I'm blasting off the remaining material with the face mill on the decal. Rotary milling. It's very fast. First tool is a 6mm bullnose end mill. Means it has a 6mm diameter, 0.5mm corner radius, and this is one of my standard tools. I keep it in a long shrink fit holder, roughing tool, some material. I use this only in aluminum and plastics or other non-ferrous metals. I divide my tooling setup between ferrous and non-ferrous materials. So this usually does not see any steels. Machining on this side, there is not much stock to be removed, so this 6mm cutter is doing perfectly fine. And most of it is an adaptive strategy, keeping the cutting forces low and feeds reasonably high. And I'm also using this tool to finish some areas of the part already. 2mm 2 flute relieved or necked to 10mm depth of cut. The 2mm cutter is doing all the internal finishing, both walls and the floor finish. Going a little bit slower so I don't get funny chatter marks in the internal corners. 4mm ball nose. I do have a 90-degree tool for deburring and chamfering setup, but I still prefer to cut counterbores with ball end mill. The result is so nice and it's super fast to program, so why not? A long series, a very long series. Well, it's a normal flute length, but very long necked 3-flute carbide end mill with a zirconium oxide coating, if I remember correctly. These work quite well. They are horrendous expensive, but they work quite well. That's a Hoffman tool. This was kind of annoying, using the super long tool to cut this side of the stock. I could also set it up on the manual mill and just cut that side with the face mill, but it's a CNC mill, it runs on its own. I went away and did something else. Box standard 4mm 90-degree spotting drill. Spot drilling deep enough so it leaves the correct sized chamfer for tapping after drilling. Tap drill for M2. It's a 1.6mm coated high-speed steel drill. Didn't have a carbide drill here. I like to do on router style machines a full retract drilling because these machines are not great at drilling, to be honest. 2mm carbide drill. This is a PCB drill. Very inexpensive but super effective. Chamfering tool, 6mm 90 degrees. These are quite cool. These are spiral flute deburring tools. When you look at the cutting edge here, you can see that it's an arced or a bowed cutting edge. That's the function of it being spiralized. These work quite nice. I really like these. They're not super inexpensive. Hoffman sells these. I think they are like 30 bucks a piece. But if you don't push them like crazy, they last very long. Putting a tiny edge break on every edge that this tool can reach. There is almost no manual deburring or chamfering left on the inside of this part. Cleaning everything before pulling it off the 0-point plate. And you might notice that the enclosure of the machine is not a cardboard box anymore. It has evolved. It's now it's now MDF, the wood material, the wood composite. I was considering building one out of sheet metal, have the part laser cut and bent and bolt together like IKEA furniture, but doing a good sheet metal construction is quite the effort. So I figured I'd just have the parts cut as far as possible at the home improvement store from 6mm MDF and assemble it with polyurethane glue and triangular wooden strips in the corners. And here you get a full view of the enclosure. It still lacks the door that will fold up, but I will do that sometimes else. So I built it out of MDF. As you can see, I have those triangular strips of wood glued into the corners as reinforcement here too, and also on the inside. Then I spray painted it very thick with gray polyurethane paint, and I'm quite happy how it came out. Cost me less than 100 bucks including the paint. Let's get the pull studs out. So these go in the ultrasonic cleaner. They are absolutely reusable. A real CNC machinist wouldn't do this. I'm going to bandsaw away most of the stock. If somebody with a 5-axis machine or with a mill with a lot of spindle power would do these parts, he would just rough away the material. But for me, bandsawing is very economical, it's very cheap and fast, and I can get rid of quite a bit of material. Over at the surface plate, I'm laying out the lines for bandsawing, and it happens to be 25mm from this surface. So I rest the part on a 1, 2, 3 block, And I use a second 1 to 3 block in the 2 orientation. And this gives me my 50-ish millimeters for the layout line. First part. And that's why I cut the large flat here, to give me something to reference off. Yeah, I'm using a felt marker on a surface plate for layout. Sue me. And the second layout is referenced off this surface. Also 50 millimeters. So just going to drop, to do it like this. And we need to bandsaw away all of this. Same on this one. Quick cat intermission, that's Ernie and Bert. Bert being the fluffy one. Using a 1 to 3 block as to adjust the squareness to a table. I added some powder masking tape to the moving jaw of the vise. I stoned everything before I started so I don't leave imprints on the part, but still, better be safe than sorry. Removed all the waste stock on the bandsaw. Now I have two roughed out L brackets. And as you can see, when we line up the part with the 3D print, the part is hidden in there somewhere, but you can already see that the contour on this side is done. Here's the transition radius that's going to this L, to this leg of the L later. So it's taking shape. Next we have to put the fixture on the mill. And yeah, I'm left with two nice chunks of aluminum. 6082 T6. Nice chunk of material. Maybe I will make something out of it, or I will dump them in the scrap bin. Chunky scrap pays better than chips per kilogram. For second sight, I need the center of the 0-point plate. I don't have the calibration artifact that Lang sells, so I'm going to pick up one of the bores and move over by half the hole-to-hole distance. Okay, that's 0. The keen observer might have noticed that there was no threading tools involved in milling the first side. I didn't have an M2 or an M4 thread mill. I just milled or drilled the holes for the threads, and I'm hand tapping them now. And for these 3 M4 threads, I can actually use my fixture as a tapping guide since it's drilled through all the way. This funny Noga countersink works way better that it has any right to. It looks super goofy when you see it first time, but they work super well. So everything is clean. And now I can use my fixture and it registers with the first side that I milled. Now I can use it as a tapping guide just by poking through with a tap like this. Sometimes I really feel a bit inadequate making precision components using a bench vise that didn't cost as much as a used car. If I had to make more than like 2 or 3, I would definitely get a thread mill and mill all the threads in the first setup. But for one-off, two-off work, well, I should be stocking thread mills anyways, but, well, thread mills are expensive. And I actually don't do a lot of traditional CNC work like this part that I'm doing in this video. That's not what I consider my main line of work. That's usually better suited for people who have real CNC machining centers and preferably a 5-axis machine, because you could make this entire part in one setup on a 5-axis and then just saw it off with a carbide saw blade. Since a friend asked me for these parts and the quote I gave him was okay for him, I got the project, and it's quite refreshing for me to do parts like this from time to time. But as I said, not my main focus of work that I strive for. This is not even a lathe part. It feels like 95% of the parts that I make these days start on a lathe. So this is quite the opposite for me. The prepared part goes on the fixture, and we do this from the back side. If we do it the right way, the holes line up too. Now this entire pallet or fixture with the lang studs can go back on the CNC mill. And everything will be aligned and on center and where the machine thinks it will be. It does not hurt to hit the 0-point plate with a ground stone just to make sure there is nothing sticking up. There we go. Fixing it down. Oh, you might notice that the mount for the MQL system has changed. I quickly 3D printed a little adjustable bracket that allows me to tilt the nozzle wherever I need, but it's always on center line in Y direction. And the last tool in my collection of tools that should not belong in the spindle, because they are all very long. This is a 10mm single flute end mill from Datron. and I necked it down so it allows me for a stick out of 46 millimeters, or a relief length of 46 millimeters. Stick out is even a little bit longer. The Datron single flute end mills really work quite well, but they make a terrifying noise when they run. The Datron single flute cutters really work very well. They are not a cheap tool, but they work very reliable. So this part with my approach requires fairly long tools on the second side. You could put it at a 45-degree angle and treat it like a full 3D part. So it sits like a V on the table, and you reach from above into the V shape for surfacing everything. It's probably slower from a machining time, but you don't need so ridiculous long tools. The same Datron end mill will do the surfacing too. It doesn't have a corner radius, but if you go 90 degrees to the orientation of the radius, it still gives a very nice finish. With a fairly small step over, of course. I think I did a 50 micron step over here. Cutting the large chamfer. The 6mm bullnose end mill from earlier, in its shrink fit holder, barely cleared the vertical portion of this part without crashing into it. I verified that in the simulation in Fusion before I started it. That's the benefit of having the tool holders modeled in the CAD system. Second side done, looks quite good. And as you saw, some of the clearances with the long extending tools are a little nerve-wracking, so I just leave. I'm pleased how it came out so far. All the blends look good. Okay, let's get it off the machine, put the other one on. That's both of the brackets machined on first and second side. Next, we have to cut these cavities and drill all the holes in this side of the part. For that we have to stand them up like this. For the third side setup, I have a 1-2-3 block and one of the smaller Moore setup blocks in the vise, and a piece of an M8 clamping stud. Part goes over the stud, and then I add a stack of washers and a nut, and the part rests on the smaller block. Here you can see the part when I loosen the nut can drop on this block here, and it gets aligned in this orientation, and also side to side. But side to side is also ensured by the squareness of the 1, 2, 3 block down here. Then it's just a matter of tightening the nut. Speaking of torquing things, that's all it needs. That's the amount of torque I'm going to put in this. This is plenty for what I'm doing. No need to squeeze the life out of everything. I need to pick up a 0. I think when I programmed it, I've chosen this back corner as my 0. Picking up the rear left corner of the part using dial test indicator. I've shown this procedure numerous times, and I have a detailed video on how to do it, so I'm not going to explain it again here. But I really like this method. It's relatively quick and super precise, since it doesn't rely on the run out of a 3D probe. I mentioned the term standard tooling now several times, and well, that it's basically tools 1 to 8 in my tooling library that never change. Tool 1, for example, is a 1mm ball end mill with a 6mm shank. Tool 2 is always a 6mm chamfer mill. Tool 3 is always this long series 4mm end mill. Tool 6 is always a 1mm 3-flute carbide end mill. Or tool 8 is always a 6mm 3-flute bullnose end mill with 0.5mm corner radius. And these tools are all set up in Fusion with their designated tool holders. The stick out does never change. These are really fixed in, and they're this is not a universal tooling setup. Most people would look at these and just shake their head, but they're catered to my needs and to the work I do. For example, tool 5 is a long necked 2mm end mill for steel. My roughing tool in this case is a long series or long necked down 4mm 3-flute carbide end mill for aluminium. Again, this is one of my standard tools. Didn't have a 2.5mm carbide drill, so I'm using the skewering coated high-speed steel drill. Second one done. That's all the CNC machining on these parts. And while I'm tearing down the setup, I want to quickly talk about one of the most important and often overlooked pieces of support equipment in a machine shop, and that's the humble air gun. I really do not know how people without compressed air in a shop work, actually. You have, for example, setup hardware that's covered in oil and chips when you're done. I really need or want to blow the tools chip free when I'm done. Same, 1, 2, 3 blocks are particularly annoying because they have a lot of holes. This ensures both a certain degree of cleanliness and precision. One thing that I should say, compressed air is darn loud. There are noise-reduced blowout pistols or blowout guns. I do not like them because you can't pinpoint the air. I wear hearing protection when I use the air gun. The noise-reduced ones are very good in an environment where more people are working together. When you use compressed air, try to be smart about it. If there is a pile of chips, do not hold the air gun in and just give it a blast. That will just spread the chips all over the place. Use a rag to contain the mess. Most of it will land in the rag. I mentioned it before, I mention it again. Cleanliness in a machine shop is really, really important for me. I'm in here several hours a day working on either hobby projects or, well, trying to make a living. And I just think it's important, at least for my mental well-being, to work in a clean, semi-tidy environment. When I'm right within a day, within a project, it gets out of hand very quickly and there will be piles of tooling on the tables. But I will make a very, very good effort to clean the shop every day when I'm done. The cleaning process is also kind of an inspection. You just notice things that are loose, or you might notice wear. You can include your preventive maintenance, like greasing the ball weight trucks of the CNC mill, things like that. And when you do this on a regular basis, it usually does not go into full fallout mode, and it stays manageable from a cleaning standpoint. So I think that's fine. Countersinking all the holes for tapping. So also a quick mention, in my opinion, the best drill press vise is for precision work, of course, not if you're a fab shop. For general precision machine shop work, is a grinding vise. A better CNC machinist than me would have chamfered the holes, of course, in the CNC. So since I don't have a flex arm, tapping arm, I do all my guided tapping here in the drill press. And what I started to do is I grind a square farther up on the shank of the tap, so I can grab the shank like this in a tap holder. Means I can use the drill press as a guide for the tap, just by opening the chuck a little bit, and then it's nice and guided. And with the tap retracted into the chuck and clamped, you can align your tap with the hole, lock down your grinding vise to the table, lock the quill, open the drill chuck, and tap away. That's 8 holes per part, 2 parts, 16 holes in total. This is a case where the tapping head, the Tapmatic, would make sense to set up, but I will just quickly hand tap them. So one thing about CNC machining, of course, from a productivity standpoint and repeatability, process control, and efficiency, it's a complete no-brainer. I should do way more of my parts that I make on the CNC. I can usually be productive enough on the manual machines. I don't plan to get rich over here, and I don't want to burn myself out, and I don't want to go into huge debt for paying for a high-end CNC mill. I just be here and make cool stuff, and as long as it works out, I'm very happy. The CNC is for me just almost support tooling for parts that are either very tedious on a manual machine or I have to make a lot of parts. But if I have the option to make a part not on the CNC, I'm happy. I know that a lot of people in the comments will think different, and that's perfectly fine. That's a very reasonable decision. One person can easily run 2 machines in a prototyping environment, or even 3, and usually not get overly stressed out. For me, it's a rare thing that 2 machines run, means the CNC and I do something on a manual machine. Sometimes I just like to have the CNC run and walk away completely from the shop. I don't know, maybe I'm just not made for hustle culture, and I'm lacking the grind set. I think on a 5-axis mill, a decent caliber of a 5-axis machine, these parts would be completely finished 90 minutes, I guess. Completely. All sides finished, sawn off, deburden the machine, all threads milled, nice finishes. I don't have much illusion there that I can reach those speeds in my shop. I might be stupid, but I'm not that stupid. Programming was done in Fusion. I have not shown any of the programming because for most viewers that are mostly here for general machining content, the CAM side is super boring, I guess. Also, I'm not going super deep into the actual CNC machining content. There are way better channels for that who can teach you CNC machining better than I do. I learned CNC machining from the standpoint of a manual machinist, and that's still how I think in regards of many approaches. I usually get to what I need to do with my skill set and when running a CNC, but it's usually far from being an ideal solution. My speeds and feeds are extremely conservative. I prefer to program for first part process reliability as much as possible instead of material removal rates. If it runs on a 1 or 2 off, if it runs 50% longer than an optimized program, I don't care. I can do something else while the CNC runs. That's why it's a CNC. And I don't take too much pride into my CNC programming skills, so it's not like I need to show off there. Inspecting the thread depth or gauging the thread depth, I took a M3 screw and I jammed 2 nuts on it, leaving the length of thread that's spec'd out in the drawing exposed, so I can check if I tap the holes deep enough. If this technique is good enough for NASA, it's good enough for me. Doing 100% inspection here. Nothing is more annoying when you assemble something and there is one thread that's not deep enough. I've been on the assembly side a lot, and I had to tap a lot of holes deeper. Same technique, just guiding it with the drill chuck. But instead of a large tap holder, I just have this knurled aluminum disc that I'm using for this purpose. And this works brilliant. Super safe, very hard to break a tap that way. You have to be a little bit careful once you get to a point where the square of the tab comes out the end of the chuck and you're about to lose your guidance. The ring is very nice for unwinding the tab. Forces with the M2 tab are so low that I don't even have to clamp the vise down. Last step will be those two angled holes that start up here in this recess and break through in this cavity down here. One is 4mm, the other one is 2mm. Both are under the same angle, and it's not a compound angle, it's just tilted to one side. Over at the milling machine, I cobbled together some setup blocks to get the part in a good position. It's resting on top of this 1, 2, 3 block. There is a second 1, 2, 3 block to space it off the fixed jaw, so I don't overhang to the back side, and would mean I run out of y-axis travel. And I have a block bolted to the side of the vise with a stud and a jam nut as a stop. Just using stuff that I had laying around. So I'm just using a dial test indicator to find the center by sweeping it. I already did that off camera. You don't have to see me find the center of a round object for the 700th time. Gets a little bit repetitive. That's good. Zero out the DRO, and we will change to a small carbide drill, and I will spot drill the position of the angled holes. And since I have a stop set, I can just flip between the parts back and forth. This is accurate enough for this purpose. Let's tilt the head. I could also put the part at an angle using setup blocks, or tilt the indexing head. We have many options, but I think since I have to do two parts and I want to flip them back and forth, tilting the head will be the easiest solution. I don't fear trimming a mill head. Okay, getting it to 28 degrees. Also notice that I talk quieter when I do precision work. And in this case, there is no need for something like a sine bar to set the angle. Graduation on the angle setting here is super well done. And since the diameter of the style of the graduation of this ring is like 160, 180 millimeters, something in that region, it's very easy to set angles relatively precise just by looking at it. It's not like tool and die work accurate, but for drilling a cable passage into a part, it's fine. So I changed to a drill chuck because we're drilling, and I can simply align any small tool that I put in the drill chuck with the spot mark that I drilled in the previous setup, just by eyeballing it, and drill through with a 2mm drill. Well, I will spot at an angle first, like spot facing. Once the X position is found, you cannot move the table up and down anymore, because that would shift the X position. We don't have to worry about the Y position, because that didn't change when I tilted the head. I mean, I could even use the 3D print and just pick up the location from the 3D print with a drill like this. Switch to the aluminum part and do it that way. Would be perfectly accurate enough. Or 3D print a drill guide at 28 degrees that I can stick on top of the aluminum part and drill it either on the drill press or here on the mill. So many options, but I felt like doing it the milling machine route. Did he just put a end mill in a drill chuck? Yes, he did. And just spot facing a little bit here. So I hope you enjoyed this mix out of CNC and manual machining. Well, it was mostly CNC, but you saw the approach of somebody who thinks more in the terms of manual machining when doing CNC machining, less of a real CNC machinist approach. Real CNC machinists probably would have machined it out of solid block like this, machine everything and then saw it off here, receiving one finished part in one setup without any additional work. But for my purposes, this technique worked well enough and fast enough to be feasible. So I of course fully understand the utility and the practicality of a CNC machine. I did prototyping on CNC mills for the better part of 10 years, but I don't get great enjoyment out of doing it anymore. When I can run the manual machines, I'm happy. So thanks for watching, thanks for the support. I hope you learned something, and I'll be back.